All right, in this video, we're going to introduce vector line integrals and to help motivate the idea, let's suppose we're moving along this path C and there's a vector field acting in this region. And let's suppose that this particular field is describing wind force. And what I'd like to know is how much sort of overall does this wind act in my direction of motion, right? Is the wind at my back helping me along the way, or is it blowing right in my face, perturbing my motion? Okay, so in particular, I'd like to look at vectors of the field that are acting on points along C. And if I want to know how much F is acting in the direction of motion, then I'm going to go ahead and consider this unit tangent vector, T, to our curve. So if we parameterize C with this vector function r of t, recall from Calc 3 that if you differentiate that, you can get r prime. That's just really your velocity vector. And the velocity vector always points tangent to your path. So in other words, it's pointing in the direction of motion. Now if you divide that velocity vector r prime by its magnitude, that's just going to give you the unit vector that points in the direction of your velocity vector. Okay, so you can think of this unit tangent vector, say, as the direction of your headlights if you were driving along this road, say, late at night. Okay, so it's just describing the direction of motion. Now, if I want to know, okay, how much does my force vector point, or in other words, contribute towards this tangential direction, then what I want to look at is the scalar projection of this force vector F onto the unit tangent vector T. Okay, and this is also known as the tangential component of the vector F. And you can see in this little triangle here, okay, what we really want is the length here of this purple vector. Okay, so what I want to do, I want to take the length of the hypotenuse of this right triangle, which is just the magnitude of f, and I want to multiply it by the cosine of this angle. So in other words, I want this right here, magnitude f times cosine theta. But notice that since the unit tangent vector has length 1, this is equal to the product of the magnitudes times the cosine of angle, and that's just simply the dot product. So in other words, the dot product here is telling us what we call the scalar projection of f onto t. Okay, so what we now want to do as we move along the curve is we want to get an overall feel for how much this wind force is acting in the direction of motion. We want to sum up all of these various tangential components, okay, as we move along the curve. So in other words, what we're going to do is we're going to compute the line integral of this dot product quantity, the scalar projection quantity, over this curve C. And this integral is going to give us an overall measure of how much the curve C sees the vector field F. Okay, so what do I mean by that exactly? Well, here's a few scenarios just to compare. So let's say in a rather extreme case, the force vector always points in the direction orthogonal to our path. Okay, so in other words, F and T are perpendicular at all points along C. So that would indicate their dot product is just always 0. And so there, the line integral would be 0. Okay, how much of the curve C would see the field in this case? Well, it wouldn't really see it at all, right? It's always acting in this perpendicular direction. Okay, if I were to take the shadow of F onto T, I'm just going to get the 0 vector. All right, so now what about in the second scenario where the angle formed by the force vector and the unit tangent vector is acute? Okay, so if theta is between 0 and 90, cosine's positive, so my dot product there would be positive. And I can see here, right, that this wind force would be helping me along as I move forward along C, right? So the wind would be at my back here. And I would be, the curve C here would be seeing the vector field. Okay, again, if I were to project F onto this tangential direction, okay, there will be some, in this case, positive tangential component. Okay, now here, if for this third scenario, the angle between your force vector and the unit tangent was always between, say, 90 and 180. Okay, so you had an obtuse angle there. Then the cosine's negative. Okay, so your dot product is going to be negative. And now I can see that the force is acting right against us, right? It's going to be perturbing our motion, making it harder to move along C. And in this case, the line integral would come out to be a negative value. Okay, so this scalar projection, although I did say it's the magnitude of this purple vector, it would be actually the magnitude in the case you have an acute angle. But that is a bit of a lie, right? Because if the angle is obtuse, like you see here, this scalar projection can come out to be a negative quantity. Okay, so you can think of this as like the signed magnitude, really, of that shadow vector in the tangential direction. Okay, great. So now let's go ahead and talk about how to go and compute one of these things. Get rid of all these layers here. So let's say here's my curve, and I have my unit tangent vector, which again is just r prime over its magnitude. Here's my force vector. If I want to compute this line integral, well, just like we have been computing line integrals, what I want to do is I'm going to evaluate my function here, which happens to be my vector field f, along this path, which is being described by this vector function r of t. T here, the unit tangent, I'm just going to replace with this expression, right? Just r prime over its magnitude. And then ds, remember, that's just the magnitude of the derivative vector times dt, right? Just speed times time. So if I put all that in, I'm going to get f, again, evaluated r of t. There's the unit tangent vector expression, and there's our ds. And of course, now we see that this magnitude of r prime is going to drop out. And so we get this expression, okay, which is going to give us an integral with respect to this parameter t, as we let t vary from, say, a to b. And we're just taking our vector field f evaluated at this vector function r of t, and we're dotting it with the derivative vector. Okay, and this is the main way we're going to go ahead and compute these things, and we'll illustrate this in the next video. What I want to say at the very end, though, here for this video is just there are some other notations that are commonly used for vector line integrals. And so these first two are just what I have up above. But notice here that r prime of t dt, well, that's the same thing as just dr dt times dt. Okay, so getting rid of the dt's, that's really just dr, right? D, the vector r there. So sometimes you'll see this notation f dot d vector r for the vector line integral. And now if you're thinking in terms of components, okay, if I call the components of our vector field, say pq and dr, well, that's just the differentials of our x and our y components. Okay, dotting those together, I'm going to get p dx plus q dy. Okay, this is another really common notation that we're going to see a little bit later. All right, so again, in the next video, we'll illustrate all of this with some examples. All right, see you then.